In this video, I'm going to go over a few of the basic concepts behind neural networks and to understand what motivates us to use neural networks rather than traditional machine learning. So firstly, I'm just going to do a quick recap on supervised machine learning. In this module, we're going to talk mostly about supervised neural networks. And when we have supervision, that means that we've got supervision labels. So if we have a dataset X, let's say we have 3 images in dataset X. These are going to be X1, X2, and X3. So for supervised learning, we know what these images are. So let's say that this is a dog, this one's a cat, and this one is another dog. And we're going to call these labels Y. So the dog is going to be Y1, and then cat is going to be Y2, and then the dog again is going to be Y1. So supervised learning is just when the machine actually has access to these labels Y1 and Y2, and it knows which of the images are which, and that's during the training phase. So obviously during the testing phase, it doesn't have access to the labels. So what a machine learning system is going to do, as a quick recap, in the real world, there's going to be a perfect function f star that can map from x, whether x is x1, x2, or x3. It's going to be able to map from that x to the correct label y. So that's the perfect real-world function. And what we're trying to do is discover a new function f which can do the same. So our neural network is going to be this function f, and it's going to give us outputs y dash, and the idea is we're going to try and minimize the distance between the labels that f gets compared to the real world labels. You can also think of this as very similar to the human brain. So hopefully, if you see an image of a dog, if you see image X1, your brain will be able to compute that image and tell you, that's a dog. That's exactly the same sort of thing that we're trying to teach a neural network to do. So why do we want to use neural networks compared to traditional machine learning? Let's look at the pipeline of a traditional machine learning system. First, you'll input your image, and then you'll have a human that designs features to extract from the image. Then you'll do your classification based on those features, and finally you get your output, which will hopefully be correct. The difference with a neural network is that it combines the feature design, extraction, and classification all in one step. So the machine is actually designing the features to extract from the image rather than having them been designed by humans. And we find that this is much more powerful when you remove the humans from the loop. So there's a couple of more reasons. There's a couple of reasons why that occurs. The first is that you're asking the machine to do the classification, so it knows best what representations are going to be most powerful for it to classify. So it's much better for the machine to be able to learn that itself rather than for a human to do it. In general, we find that any singular task that we ask a machine to do, the machine performs better than the human. So why not actually ask the machine to design the features in that manner as well? And that's exactly what we find when we try to get a machine to do this. It it designs much more powerful features and performs much better at doing this job. The second thing, which is really, really important, is if you get a human expert to design some features for you, let's say, that expert will have some biases, whether they are known or whether they're unknown. The expert will have biases, and those biases can be encoded within the features. And because the machine is actually going to learn these features from scratch, those biases aren't going to actually be present in the final neural network that you have. There will still be some biases. They usually come from the dataset. Sometimes they come from the design of the architecture. So it's not the case that a neural network is completely bias-free. But what you are doing by using a neural network compared to a traditional machine learning architecture is you're eliminating one of the main sources of bias, which is a really, really important thing to do, both to get better performance and to be able to use your machine learning system in the real world, because that bias isn't there. So the key way that a neural network can learn to classify information is by developing powerful representations of the original data. And we're going to talk a little bit later on in a different video about how exactly it does this, but I just want to give you the underlying concept in this section of this video. So let's say we have a human face because it's easy to draw. And let's imagine we're trying to do some sort of emotion recognition on this. So bear in mind that this image, often images of human faces will have a height of 256 and a width of 256. And this will also have 3 channels because it's in color. So you'll have red, green, blue, like that, which means that your full dimensionality is going to be 256 by 256 by 3. So there's almost 200,000 pixels that you need to consider here, which is a ridiculously high dimensionality. It's way too complex for any machine with current technology to directly derive information from, or at least derive powerful information from. So we want to represent this data in something much smaller, ideally something which looks like a 128 by 1 vector. So we're going from a tensor, which is almost dimensionality of 200,000, to a vector which has 128 dimensions, which is a lot easier to process. And this is a very nice example of this, which demonstrates this concept. And this figure's from Deep Learning book, which I highly recommend that everybody watching this takes a look at. And just for those of you that haven't seen polar coordinates before, what's happening here is we have 2 classes. The first class is a bunch of blue circles. The second class is green triangles. And we'll say that this is the origin here, 0, 0, as where it usually is. And you've got the x-axis as usual and the y-axis as usual. So these are Cartesian coordinates. So we can represent this data in a new way to find a better class boundary. This class boundary at the moment, it's clear for a human, but it could be made more simple. So what we're going to try and do is to represent this data in a new way to get a much simpler understanding of the data so that we can separate these 2 classes with a single straight line. And the way we're going to do this is we're going to get rid of the initial origin, and we'll instead draw a new origin in the middle. And we also draw this imaginary horizontal line across to the edge of the axis. What's going to happen for each of these points is we're going to select the point and we're going to draw a direct line to that point. That is going to be the radius r. So we calculate the distance to this point, and then we're going to also get the angle theta to this point, and then we're going to plot these as the new coordinates on the second graph. So we move, so this this origin here is going to be the bottom left origin on this graph, and we just go across by r and then go up by r. And what we see by, and go up by theta, sorry. And what we see by representing the data in this way is that because the maximum distance of any of these blue dots is less than the minimum distance of any of the green triangles, we can actually separate the data by this nice straight line. So a neural network is going to try and do the exact same thing. It's not going to convert things to polar coordinates, but it's going to try and find different ways to represent the initial data so that it can make these really easy decisions by which class the data is. If we go back to our initial example where we have faces that we're trying to classify with different emotions, we're going to try and represent these images in these 128 by 1 dimensional vectors, and we will place these on what's called a manifold. So what you should end up seeing is all of the faces of someone smiling should end up in this manifold when they've been converted to 128 by 1, and then in a different quadrant of the manifold you'll have people that are sad, and then over here you might have people with a neutral face, and then in the other corner, I don't know, maybe you'll have someone with a shocked face. And that's how the machine will be able to classify between different emotions, because it has these very nice decision boundaries here that are just done by straight lines. So this is a really nice visualization of what one of these manifolds might look like from the paper In Defense of the Triplet Loss for Person Re-Identification. And you can see, for example, that all of the striped shirts tend to be down towards the bottom. So this is one of the features that you end up with when you convert from a, in this case, it's a 128 height and 64 dimensional width. When you convert to just a 128 by 1 vector. So you can see clearly that one of these features is to do with the stripes that you can see on the shirts, and then here you also have a difference where you have all the horizontal stripes on the right side of this boundary and the vertical stripes on the left side of the boundary. And then as you move upwards as well, you can see that different coloured shirts are grouped together. So you have one of these features is going to be whether stripes exist. Another feature is going to be what direction they're pointing. And then as you go up, you're going to have more things like the colour of the shirt, whether you've got bicycles in the picture. You'll have things like handbags as well, and just additional objects. And these are all inherent in these features that we don't see. So I think the key thing that we need to remember when we look at one of these manifolds, these images have been placed on the manifold only because they've been able to be converted into this low dimensional representation and then placed on the manifold. You wouldn't be able to do this with the initial image. So We're going to see how you do this in a future video, but first we're going to discuss some of the limitations of neural networks.